Assalamualaikum warahmatullahi wabarakatuh. My name is Mohd Zahin Nur Khalis Bin Awang Adi from RY31. Today I would like to show a demonstration of this lab 6, which is Ziegler Nichols tuning method. This method is used to find the value of the PID controller, and the equation of transfer function given is this: 6 over s plus 1, s plus 2, and s plus 3. And the first thing we do here is to do the calculation to find the value which we use in the MATLAB. And from this calculation we will get the value of 1, 6, 11, and 6 for the denominator, and numerator is 6. And the value of feedback is 1, which is the unity feedback. And the GS equal to transfer function numerator denominator, we will get this function, and after we add the feedback we will get this function. And first we will run this system without the controller. Here we get the step response for the closed loop system without controller, and we can get the characteristic of rise time, which is 1.15 seconds. The overshoot is 9.58%, and settling time 3.68 seconds, and the final value is 0.5. And then we can observe the result of the simulation here, which is the same as the theoretical calculation. That's for the without controller system response. Next is we add the proportional controller into the system. Here we get the value of Kp equal to 5 from the calculation here, where the value of 0.5 constant multiply with the K we get from the real part calculation. We get this value from the characteristic equation, and then we will get the value of Kp equal to 5. Ki is 0 and Kd is 0 because this is the only thing we use here is the proportional controller. And same as the previous one, we use numerator 6, denominator 1, 6, 11, and 6 because this is the main transfer function, and the feedback is 1. We use this controller here equal to PID, Kp, Ki, and Kd. And then we add the PID controller into the system, and then we plot the step response. Here we will run and we'll get this step response, and we'll see the value of peak response, settling time, rest time, and steady state. Here we will get the value of rest time is equal to 0.504. The overshoot is 54.9%. Settling time is 9.01 seconds, and we get the final value, which is the steady state error of 0.83. It is almost nearly to the perfect steady state error. And we'll see the result of simulation here. We get this value after we add the P controller here, and from the calculation we'll get this one after we add the Kp into the controller. This is the transfer function for the P controller. Okay, next for the PI controller, we get the value of KP 4.5, KI 2.86. From the calculation here, 0.45 is multiplied with 10, which is K, and Ki we get from this formula 1.2 multiplied by Kp over PCR. PCR is this one, 2 pi over omega. We get the value of omega is 3.32, and we get the PCR equal to 1.89, and we get the value of Ki is 2.86. We put it in here for the PI controller, and we will plot the step response for the PI controller. We will run. Here we will get the result of step response. Here we will see the rise time increase a little bit and overshoot increase a lot to 63.2%, and the settling time became even longer because of the eye controller, because the eye controller make the transients respond much more slower. But the advantage of eye controller, we will get a steady state error of 1 here. This is for the PI controller. Okay, next we will see for the result of simulation here, which is the transfer function for the controller added with the main transfer function. We'll get 24/7s plus 17.16 over s power of 4, 6s cubed, 11s squared plus 33s plus 17.16. We get this from the calculation here, the transfer function, after we add the Kp and Ki into the transfer function. Okay, next for the PID controller. For the value of Kp, Ki and Kd, we get from this calculation based on the Ziegler Nichols formula. We get Kp equal to 6, Ki equal to 5.67, Kd equal to 1.42, and we put the value into the MATLAB and use this function for the controller PID, Kp, Ki and Kd, and we plot the step response graph. Here we will get this graph, and as we can see here, the value of rise time decreased to 0.449 seconds, and the overshoot decreased a lot from 63% to 40%, and settling time is decreased a lot from 17.7 seconds to 4.77 seconds. In PI controller, it took much more longer time for the system to reach the steady state, but here we add the D controller into the PI controller, because the derivative controller have the effects of making the system much more stable and decrease the settling time. And here we get the steady state error equal to 1. And as we can see, the value of transfer function here for the PID controller, we get from this calculation, which means the theoretical calculation is the same with the simulation. And next here we add all the coding into one, so we can see and compare all of the difference between each of the controller for P, PI and PID. We'll run here. The blue one is the system without any controller. And here we can see the P controller, where we get the steady state error equal to 0.8, not not that perfect yet. And for the PID and PI controller, we get the steady state error equal to 1. But here we'll see the PI controller have much longer settling time, which is equal to 17.7 seconds. And here the PID controller have the shortest settling time, equal to 4.77 compared to the other controller. And the PI controller have the highest overshoot percentage, which is 63.2%. And among the three controller, we can observe that it can be observed that the PID controller have the best performance among the three. And that's all from me. Thank you.